Alright, so today we're going to be talking about one of my favorite topics in pre-calc, which is going to be piecewise functions. The reason that it's one of my favorite topics is that it combines a lot of our previous knowledge from Algebra 2 and Algebra 1 kind of all together. It's also a newer topic. Some of us might have seen it a little bit depending on where we went and how Algebra 2, and some of us might not have. And that's okay. We're going to kind of make sure we're all on the same page. So a piecewise function. Now it sounds kind of funny, but basically what it is it's going to be a type of function that contains two or more equations over a specified So we can kind of think about each of our equations as the pieces that make up the entire function. And that's why it's called a piecewise function, is because the function is made up of multiple pieces. So we can't have one that just has one piece because then it's just a normal function. So that's why it says two or more. Some of the equations that we look at, some of the functions that we look at will have two, some will have more. You are actually going to be starting your project over piecewise functions, and your function is going to have to contain at least 6 pieces. And so this is what a piecewise function looks like. We have f of x, so it's still a function, so it still gets the f of x notation. We put equals, and then it gets kind of this fancy interval on the side. And so then each of our pieces or equations is going to be listed. So like on this one, I have x squared plus 1 and x minus 1. And then the part that's a little bit different for us that we haven't seen before is what we were talking about when we said that specified domain. And basically that's what this comma, x is less than 0, or comma, x is greater than or equal to 0. Those are the specified domains for each of those pieces. And basically what it's saying is I want to use the equation x squared plus 1 if x is less than 0. And I want to use the equation x minus 1 if x is greater than or equal to 0. So this question asks us to evaluate at a couple of different places. So our first one is -1. And basically, we're going to do the same thing that we've been doing. We want to plug that -1 in for our x. However, we have to decide which equation we need to use. So on our first one, we have a -1. Well, notice we want to say, okay, -1 is less than 0. So that tells me that I want to use my first piece. So I'm going to plug in -1 into our first piece, and notice that we get 2. And it doesn't matter about what we get out because that's our y value. It only matters what we plug in because the restriction is on our domain or the x value, not the range. So if my x value or what I'm plugging in is less than 0, then I need to use my first piece. So notice that on our second one, we're finding f of 0. And we need to be careful here because only one of our restrictions can have an equal to bar. If both of them have an equal to bar, then it would no longer be a function. And that's going to be important when you start doing your project. You can only include an equal to bar on the numbers that overlap in one of the spots. Because then if I'm going, okay, 0, where do I want to plug that in? If both of these had equal to bars, I wouldn't know where I wanted to plug it in. But this time, because my equal to bar is only with my bottom one, we know that I plug it into the second piece. And then lastly, we want to plug in 1. Well, notice that 1 is greater than 0 So that tells us that we want to plug it in to that second piece. And that's evaluating a piecewise function. So on this next one, again, they ask us to evaluate. So I'm going to have f of, and we want to plug in 0. Well, notice 0 is less than 1, so that tells me I want to use my first piece. Well, 0 squared is going to be 0. 0 times anything is also 0, so I get 0. Then we want to plug in a 1. If I look at my 1, well, my 1 is equal to 1, and the only one that has an equal to bar is my second piece, so I know that that's where I want to plug in my 1, so I get 3. And then lastly, if I plug in 2, we'll notice 2 is greater than 1, so that tells me that I want to plug it into that second piece, and I get out 2. And you could do that with things that have even more pieces. Basically, you're just looking at which interval is the x value that I'm wanting to plug in a part of, and then that is the equation that you would use to plug it into. So we evaluated some piecewise functions, and we can also graph piecewise functions. Now, when we graph piecewise functions, it's going to be very similar to the graphing steps that we've been practicing with our transformations. Basically, now we're just going to combine them. So usually the way that I want to have us look at it is I'm going to just draw the whole graph of each of my pieces first. And then basically we're going to try and kind of erase the parts that we don't need. So if I were to just take the piece 2x plus 3, well, 2x plus 3 is a linear graph. It is in slope-intercept form. So our intercept is going to be a positive 3, and our slope is a positive 2. So our graph would look something like that, pretending that my line is nice and straight. And then our second piece is going to be y equals negative x plus 4. Again, it's in slope-intercept form, so we're going to go up to 4, but this time we have a negative 1 as our slope. So our graph, again, pretending that my line is nice and straight, would look something like that. But now notice that if I were to just leave that function how it is, well, it's not a function because it does not pass my vertical line test. My purple and orange lines are going to create problems. I can't have those 2 points stacked up on top of each other. And that's where those restrictions or those domain restrictions come into play. Basically, I want to kind of erase or think about only using the part of the graph that it tells me to. So my purple graph is the whole graph of 2x plus 3. I only want to use the part of 2x plus 3 where x is less than or equal to 1. So I'm going to go over to my 1, and I want to go up to my purple graph, and I want to use everything such that x is less than, which is going to be to the left, or equal to 1. And so I know that I'm basically using that whole left part of that graph. Then for my negative x plus 4, I want to use everything of x is bigger than 1. So again, I'm going to come to 1. I'm going to go to my orange graph this time. But we have to be careful because notice that I don't have an equal to bar on 1 this time. So I know that my 1, or the point at 1, is going to have to get an open circle. And this time, because it is greater than, it's going to be everything that is to the right. So that green graph would be our final graph, would be the actual graph. The orange graph and the purple graph were just kind of tools to help me figure out what my graph would look like. But then the green graph would be my actual graph. On our next example, we'll go ahead and erase the other parts so we can see what it would actually look like, but I wanted to leave them there on the last one so we could kind of see where I'm getting those pieces from. So on our next example, again, we have two pieces. I have an x squared and a 2x plus 1. Again, let's just start from graphing each piece by itself. So I'm going to graph x squared. Well, x squared is one of our parent graphs, so we should know our graph is a parabola. It goes through 0, 0 is my vertex. I have negative 1, 1, 1, 1, and then negative 2, 4, and 2, 4. So our graph would look like that. But now we're going to go ahead and erase the part of the graph that we don't need. So we only want the portion of the graph where x is less than or equal to 1. So I'm going to go over here and say, all right, I'm at 1, and I want to keep the part where x is less than or equal to 1, so that's going to be to the left. So then basically I need to erase everything else. So that's the portion of the graph that we would want to keep. Then going on, I'm going to do the same process for my next point. So I have 2x plus 1. This is going to be a linear graph. So I'm going to go up to 1, and then I'm going to have a slope of 2. Oops, sorry, I'm going to go up to 1, and then I'm going to have a slope of 2. Now notice that if we connected this line, it would keep going all the way through. But notice that our restriction says that I only want the part of the graph where x is greater than 1. So if I'm at 1, I only want it starting at this point and then to the right because we're greater than. So remember, greater than means to the right. So I'm going to erase that initial little part. I just drew that to help me make sure that my linear graph looked correct. Then I can just kind of erase it. But be careful on this one because notice that our 1 does not have an equal to bar. So that means that my 1 does not have a filled in line on my graph. So that would be the graph for this PieceWise function. And if we had more pieces, then we would just continue on erasing and adding the different pieces as we needed them. All right, so next up, we're going to look at a couple of functions and decide if they're continuous or not. All right, there we go. We can see them a little bit better. So it says decide if the function is continuous, and if not, change the value so that it is continuous. Now, on most of the examples that we looked at before, none of these were continuous. They didn't line up. I would have to pick up my pencil to continue on. And there will be some cases that they will be continuous. And so we need to figure out how to find that. One way would be to graph it. But notice, like in my first one, I have x squared minus 3x plus 2, which wouldn't be super fun to graph just by itself. So there is a way algebraically to check and see if something is continuous or not. And the way that we're going to do that is basically these points right here, or these boundaries, are going to be the spots where our graph would potentially overlap. And in order for them to be continuous, they actually have to meet up at those x values. So the way that we're going to check that is just by plugging in those values. So notice that if I plug in 1 into this first piece, I get 1. If I plug in that same value into my second piece, I also get 1. So notice, therefore, this is continuous. At least that portion of it would be continuous. In order for the whole graph to be continuous, we would have to do the same thing with the next piece that overlaps, which would be at 2. So we need to plug it in to our second piece, and we get 0. And then we would need to plug it into our third piece. So notice that we would get 4 minus 6, which gives us negative 2 plus 2, also gives us 0. Therefore, this piece is continuous as well, which means that the whole function is going to have to be continuous. And if there had more pieces, I would just keep going until I ran out of pieces, basically. So it said to decide if it was continuous. This one was, so I don't have to do anything else. I'm done. Kind of nice. On my next one, we're going to do the same thing over again. The only difference here is that I only have 2 pieces, so I only have one restriction that I have to worry about, and it's at 2. So I'm going to plug in 2 to my first piece, and I get 2 minus 1 gives us 1. 1 squared is 1. On my next piece, I have 2 plus 2 gives me 4. Well, notice that 4 does not equal 1. Therefore, this is not continuous. And just be careful, because even if I get 3.99999, that doesn't equal 4. As much as we want to round it, as close as it does not actually equal 4. And I say that because on your projects, you're going to have to show me that your graph is continuous. And 3.999 is not going to cut it. It's going to have to be 4. So notice that now it says, okay, if it's not continuous, how can I change the function to make it continuous? And we actually only want to change one piece of it. So let's look at what this graph would look like. So I'm going to pull up Desmos. I also wanted to show you how you plug in things into Desmos to make it a piecewise function. So you can either write it as y equals and then write your piece, or you can just write the piece of the equation itself. Either way, it's going to be fine. The biggest key is you want to use kind of the fancy or the squiggly bracket, which is right below your plus sign on your keyboard. And then you're going to put in the restriction that you want to apply to it. And your Desmos board does give you stuff with equal to bars, so you can use those in order to apply your restrictions. Because then when I graph it, notice I have a parabola and it goes ahead and stops that graph for me at 2, which is kind of nice. Then I don't have to worry about it. And so this is going to be a good way to check for yourself. Or you can also do your rough draft for your project in Desmos. So then I'm going to look at my next piece. Well, it's easy to see that these are very much so not continuous. My pieces don't line up. So what needs to happen is I need this point right here to line up with this point right here. Well, we can't just draw a vertical line, because now that's not going to be a function, because a vertical line would make it not a function. So there's kind of 2 different ways that we could approach this. We could either say I wanted to shift this whole thing up, so that would be 1, 2, 3. So if I added, let's say, a plus 3 to the outside, notice that those look like they line up. Now, that doesn't necessarily mean they line up just because it looks like it lines up. We need to verify that algebraically, and we could. But notice that in our directions, it only wants us to change one value. A value means one value. And I'm going to say that the easiest way to go about doing that is, and we talked about this in our transformation notes. So remember that I said that when we have a function, that a value is what's going to stretch or compress it. And this is where that a value is going to become your best friend. So that a value is going to allow me to stretch my graph so that it meets up with my other graph. And the way that we figure out the a value that we want is by plugging in the other information that we already have. So I know that I want to plug in my 2 value still. And when I plug that 2 value in, I need to get out 4, because I need it to line up with that second piece. And so if I simplify now, 2 minus 1 gives me 1. 1 squared is 1, and then I just get a. So notice, then I would put a 4 in my equation. And that's going to make them line up. And if we don't believe me, let's go ahead and verify that if I were to put that 4 there, look, it's magic. They do line up now at that point. And again, though, for part of your project, you are going to have to go through these steps of plugging in those overlapping restrictions and showing me that they exactly get the same number. Not really, really close, but exactly the same number. And in the next video, I'm going to go into a little bit more about those directions on the rest of that project. But just realize that your project is going to be over piecewise functions.